Hey, AP Calc students, time for more FRQs. Now, you probably think FRQ stands for free response questions, but little did you know, it's actually fun response questions. New information. Well, then again, I guess the word free is right there, so it's not fun after all. But it is fun. So here we go. AB 2016 number 4. Now, this type of question, it's a dead giveaway when you see the actual question. These fall under the style of differential equations because what you have is a differential equation. And also having a blank slope field there is a hint that you're probably going to have that. Now, depending on your teacher, your differential equation expression actually can be defined multiple ways. So in the original question here, when it says consider the differential equation dy dx is equal to y squared over x minus 1, there's a few different ways to interpret that. You may have looked at that and said, well, yeah, that's a differential equation. But it's possible you looked at that and said, well, that's just one of the three main notations for a derivative. So this is a derivative. Well, that's true too. And if you know what a derivative is, it's the formula for the slope of the tangent. You could say, well, isn't this the slope of the tangent of the function? It's that as well. So what the AP loves to do is give you the same information multiple ways to see if you know your vocab and know the context. So in this particular context, it's a differential equation that we'll eventually be solving, but also that it's the formula for the slope of the tangent. Now, the reason that that's so important is that below here we have to create a slope field. Well, if this is the formula for our slopes, all we have to do is put in our coordinates to actually get a value. So what it says here is, on the axes provided, sketch a slope field for the given differential equation at the 6 points indicated. So all you have to do is take each coordinate of the 6 points here, substitute it into your formula for slope, which is what a derivative is, but it's also a differential equation. It's all those things. So let's just start at the origin. So obviously the origin is 0, 0, so I'm going to substitute that in, and I'm going to put these values down here just so we don't have any misunderstandings. So again, dy dx is equal to, they give us y squared over x minus 1, and we have to evaluate it at the 6 points. So what I'm going to do is I'm going to start here evaluating it at the origin. So at 0, 0, I'm putting these values in for x and y. So that would be 0 over negative 1, so it would be 0. Now at the next point, at 0, 1, my x value is 0, so my denominator is negative 1, my numerator is 1, I would have a positive 1. And at the next value at 0, 2, my denominator is negative 1, and my numerator is 4. Oh, sorry, I forgot my negative here, didn't I? And so we are negative 4. Now if we jump over to these values here, let's see what happens at the coordinate 2, 0. So at 2, 0, my x value is 2. 2 minus 1 is 1. My numerator is still 0. My value is 0. At this value here, 2, 1, I substitute these in. Denominator is still 1. My numerator is also 1, so I get a positive 1. And now at the last value, at 2, 2, my y value is 2, so it's 4. On the bottom, 2 minus 1 is 1, so I get 4. So these are my 6 slope values, and a slope field is nothing more than a collection of short tangents, or baby tangents. So all I'm going to do is represent these in my picture right here. So at 0, 0, I'm going to make a short tangent here of a slope of 0. At 0, 1, I'm going to make a slope of negative 1. And at 0, 2, I'm going to make it steeper, negative 4. It doesn't have to be perfect. They're pretty forgiving. And then over here, this is going to be also 0. Well, now this is going to be a positive 1, and this is going to be a positive 4. So that's okay. So that's A. Do you know what a slope field is? Do you know how to create one? Do you realize that your differential equation is actually the formula for the slope? That's what they're testing you on. Let's move on to Part B. Part B says, let y equals f of x be a particular solution to this given differential equation. Or in other words, when you solve it, it's going to be y equals f of x. That can actually be a little confusing, and if you didn't read that part, you'd probably be fine. But they do tell you have initial condition of f of 2 equals 3. Important point. Write an equation for a line tangent to the graph of y equals f of x at x is equal to 2. So you should have done this many times throughout the year. Write the equation of the tangent. Well, there's two approaches here, depending on your preference. the equation of a tangent is going to be linear, so it's y equals mx plus b, or maybe you prefer to do point slope. Both are acceptable, and I'm going to do both to see which you prefer. And what they give us is they tell us that they want us to do this at x is equal to 2, so the x value is 2. And then it says here f of 2 is 3, so the y value is 3. So what we have here is 3 is equal to m times 2 plus b. Or over here, we've already got y is equal to 3, m times x minus 2. We're almost done. We just need slope. Well, if you recall from the step before, our differential equation is the formula for slope. And in fact, if we wanted, we could even go up here and we could say, well, this is actually m. It's dy dx. So I'm going to say m is equal to our differential equation, or our derivative. And so we're going to do this at the coordinate. We're going to evaluate this at 2, 3. All right, so at 2, 3, our numerator here is 3 squared, and this is going to be over 2 minus 1, so I think we're going to get 9. All right, so the slope is 9. So it looks like if we do this one, we get 3 is equal to 9 times 2 plus b, and over here we get y minus 3 is equal to 9 times x minus 2. If you prefer to do point slope, it would be that one. This one here, 2 times 9 is 18. Swing that over, you're going to get negative 15 is equal to b. And if you're a y equals mx plus b person, you'd be y is equal to 9x minus 15. Both are acceptable answers. So that said, write an equation of the line tangent to the graph at x equals 2. So we had our x value and our y value and our slope for formula, we've got it. But then it says use your equation to approximate the actual function at 2.1. Well, in case you weren't shown this, I'm going to sketch a little diagram over here to the side, which I'm actually going to erase here in just a second. Depends how much you were taught this throughout the year, but tangent line approximations can be really powerful if you don't have the actual function. So I want to give you an example. I'm just making this up. This graph right here does not represent anything in this problem, but I am going to use the point 2. So what I want to show you guys is, let's pretend this point right here is actually the point 2, 3. All right, and my tangent, I'm just going to draw it right there. Now I know this tangent does not represent this one here. Don't worry about that. I just want to show you the concept here. If this function is f, and this is my tangent line approximation, what I want you to think about is, if I went over to 2.1, I want you to see just how close the actual value is. So at 2.1, my tangent line value is right there, and at 2.1, the actual function value is right here. They're very close to each other. So what the rest of the question is saying is, since you don't have the function, approximate what it would be given the equation for the tangent. So you're going to let x equal 2.1 in the tangent, and we're going to take this y value, and it's going to be pretty close to the actual, and it's close enough for what we're asking for this question. So that was the whole purpose. So all you're going to do is take one of your values and let x equal 2.1 and solve for y. So I'm going to do that on this one right here. I'm going to take this over here, and I'm going to say, well, if y is equal to 9 times 2.1 minus 15, I wind up getting 18.9 minus 15, and I would get y is equal to 3.9. So that would be my approximation. So I would say f of 2.1 is approximately 3.9. And that's what they're looking for there. And this concept that may have been stressed during the year, possibly not. But it's a tangent line approximation. And as long as you're close to the point of tangency, we were very close to 2. It was 2.1. This will get you close to the right answer. Okay, now I'm going to get rid of this so we can move on to part C, which is the guts of the problem. So now part C says, find the particular solution to this differential equation at the coordinate 2, 3. So we're going to find the general solution and then put in 2, 3 to find the specific solution. And this is the fun part of the question. So here we go. dy dx is equal to y squared over x minus 1. So solve the differential equation. So your first step is to separate your variables. We've got to get y's together and x's together. So it looks like this side turns into dy over y squared is equal to 1 over x minus 1 times dx. Okay. Next step, golden rule of math, what you do to one side, you do to the other. We're going to integrate both sides. So I'm going to tweak this side a little bit. I'm going to integrate both sides, but I'm going to make this the integral of y to the negative 2 dy, just rewriting that. And this side I'm going to leave just how it is, the integral of 1 over x minus 1 dx. Okay? So now it's time to integrate. This one, use our power rule of integration. Add 1 to your exponent, divide by your new exponent. You get y to the negative 1 divided by negative 1. And we'll put our plus c with the independent variable side. Now this right here, many of you could just recognize this is a one-stepper of a natural logarithm. But in case you didn't recognize it, it's a little u sub. So I need to let u equal x minus 1. And du is equal to dx. So technically, I have this little mini u sub here where I have 1 over u du. So x minus 1 equaled u, and du equaled dx. The integral of this is just going to be the natural log of u, but I'll put u back in. So on this side, I'm going to clean this up a little bit. I'm going to make this negative 1 over y is equal to, this side turns into the natural log of u, which is x minus 1, plus c. Now at this point, again, many of you would have skipped this step and went right here is fine. But right here, I'm going to go ahead and solve for c, because they told us that our initial condition is 2, 3. So I'd like to solve for that c value and just get it out of the way. So it looks like I have negative 1/3 is equal to the natural log of 2 minus 1 plus c. Well, 2 minus 1 is 0. The natural log of 0 is 1. So it looks like negative 1/3 is equal to my c value. All right, so I need to go back and put that in right here. So I'm going to redo this step. Negative 1 over y is equal to the natural log of x minus 1 minus 1/3. Okay? Now I have to solve for y, so just a little kind of ugly algebra here. I'm going to put brackets around this. I'm going to move this to the denominator and put y over here by itself. So it's kind of a weird looking function here. Natural log of x minus 1 minus 1/3, and that's equal to y. And so if you're the kind of person that likes to always have y written first, you could go ahead and do that. And you could say, well, my final answer is y is equal to negative 1 over the natural log of x minus 1 minus 1/3. And there would be your final equation. So, differential equation. One of the more straightforward, probably one of the most straightforward type questions on the AP, where you're given a differential equation and you're ultimately, most of the time, you're going to solve it, and that's where the bulk of your points comes from. Little slope field question here. Do you know that a differential equation is the formula for your slope? And then can you find a tangent? So there it is. AP Calc AB 2016 number 4 differential equation. Thanks. See you next time.